So let us start. In this lecture, we continue to study Degenerate Fermi gas. In the previous lecture, we have derived the asymptotic expansion for the internal energy of the gas, which is equal 3/5 mu sub 0 multiplied by n is a particle number, plus 1 plus 5/12 theta divided by mu sub 0 to the second power. And using similar techniques, we can derive the expansion for the pressure of the degenerate Fermi gas. And divided by V, 1 plus 5/12 theta divided by mu sub 0 to the second power. Okay. Here, mu sub 0 is a chemical potential of the electron gas. It is determined by the formula mu sub 0. Okay, it's chemical potential of the degenerate gas at 0 temperature. Three multiplied by 2 by h bar to the third power multiplied by n divided by g sub s 4 pi multiplied by 2 m to the power 3/2 v, and this is all to the power 2/3. And here we assume that the ratio temperature divided by mu sub 0 is much less than 1. The value mu sub 0 is can be considered as a temperature of degeneration of the gas. When the temperature is lower than mu sub 0, the properties of gas are very different from that of classical gas. So the quantum corrections are important here. When we say that this ratio is small, we consider that we say that the gas is maybe, let's say, the degeneracy condition for the gas is well satisfied. The excessive expansions are approximate. And this squared quadratic in the temperature term is a leading contribution of the expansion in small parameter theta divided by mu sub 0. In principle, there, in principle, higher order corrections here and here can appear, and they appear effect. Now we are going to compute the heat capacity of the gas. As far as we have the expression for the internal energy, we can use the formula CV, it's a heat capacity at constant volume, as derivative du by dv, no, by theta for constant v and n. The proof is the formula is very simple. By the definition, the heat capacity, okay, that's not a good idea to prove this way. Let's note. We know that the internal energy is connected with the free energy by the relation U equals to F plus theta multiplied by S. Here theta is the temperature and N is entropy. And now we are going to compute this partial derivative. Okay, let us compute du by theta, constant v and n equals, when I differentiate differentiate free energy, I get entropy dF by, okay, it's better why not take another one, take this one is good, dF by dθ constant nv plus I differentiate by the second term by the Leibniz rule. Once the derivative by its temperature, we get entropy. And when the derivative by its entropy, we get a gradient of entropy. Okay. Now we know from the first law of thermodynamics that this partial derivative equals to minus entropy. Here I use the rule, the expression for the differential of the free energy, minus S dθ minus P dV plus mu dN. And S is a derivative of F by theta. So these two guys cancel each other. We get 0. And this term is a heat capacity. So, okay, we end the proof of the formula. Now we can apply this formula to compute heat capacity of the degenerate gas. So okay, CV. Okay. It's not a good idea. Right, okay. I differentiate here, I get 3/5 of mu sub 0. Mu sub 0, of course, is constant, and is constant. And when I take derivative, and I should take derivative of this guy. Okay, I forgot, I think, I forgot, I forgot pi squared here. Please correct these formulas. I forget pi squared here. And now I should take the temperature derivative from this guy. So one is constant, so I differentiate this contribution, and I get 2 multiplied by 5 over 12 theta divided by mu sub 0 squared. Okay, we can make several simplifications. Here, mu sub 0 and mu sub 0 squared cancel. Here, mu cancels squared 2. Now, 5 and 5 cancel each other. And here, 3 multiplied by 2 is 6, and here is 12. So I get here 1/2. And here should be pi squared.
Извините, пожалуйста, а пи квадрат у вас опять куда ушло? Вы дифференцировали у... Ой, да, извините, не заметила.
Yeah, pi squared. Okay. Now we can write down, and now we can write down the final expression. Okay, 1/2 multiplied by p squared multiplied by n and multiplied by theta divided by mu sub 0. It's a final expression for the heat capacity. Now we can discuss the physical. Okay. Let me think. Okay, now we can discuss the physical meaning of this, of the results obtained. Let us first discuss the internal energy of the Fermi gas. The internal energy is an extensive thermodynamic parameter, and it depends on the size of the system. And it's not convenient to say internal energy equals to something. When we study the properties of the system, much more convenient parameter is the average energy of a single particle. I denote it if epsilon sub over bar with bar over it, and its internal energy divided to the number of particles. So the result is 3/5 mu sub 0 1 plus pi multiplied by t squared over 12 theta divided by mu sub 0 to the second power. If theta equals to 0, the average energy of the particle remains a non-zero value, which equals to the 3/5 of mu sub 0. This result tells us that the motion of electrons, of particles, let's say, in the degenerate Fermi gas does not stop at 0 temperature. And the average energy of the particle depends on chemical potential mu sub 0, which is a function of, let's say, of the particle concentration and particle mass. And this energy, in principle, can be very high. It can be much higher. It is much higher than the temperature, the energetic temperature of the gas. For 0 temperature, the ratio of average energy and theta tends to infinity. This is the first very important difference. We see temperature is 0, but the energy is non-zero. Now let us look at this contribution. It accounts dependence of the average energy on the particle on temperature. Please note that this ratio is very small for the degenerate gas. So this addition is much less than 1. This observation brings us to another conclusion. The average energy of the particle have a very weak dependence on the temperature. Even if the temperature increases, the average energy of the particle does not change much. It increases but by a very small fraction. The fact that the energy is not zero at 0 temperature brings us to another important conclusion. The pressure of once particles move, they bite the walls of the reservoir with gas, so they produce pressure. And once the energy is not zero, the pressure is not zero too. So we have non-zero pressure at 0 temperature. Please note that this pressure does not depend on temperature, and it remains non-zero even at 0 temperature. And this quantity, as we see, can be very high if the concentration is high, and if the concentration of particles is high. So we can make a simple estimate. Please look here, mu sub 0 is proportional to the concentration to the power 2/3, and here concentration to the power 1. So this quantity is proportional to the power 5/3. In astronomy and astrophysics, the pressure of degenerate electron gas prevents collapse of certain type of stars called white dwarfs. These stars have no internal sources of energy, and their temperature reduces with time. So in the distant future, they will have very low temperature, which is comparable to the temperature of the universe, maybe several kelvins. But because the pressure because the pressure of degenerate gas acts against gravity, the stars will never collapse, even they will have very low temperature. And now let us consider heat capacity. Let me write out the expression for heat capacity again. Okay. Heat capacity again. C sub V equals to 1/2 pi squared n divided by theta sub nu 0. At first, we see that the heat capacity is proportional to the temperature. This means that at zero temperature, degenerate gas will have zero heat capacity. This is a good news because the third law of thermodynamics says that the heat capacity should tend to zero for low temperatures. It is interesting to compare the value of heat capacity of degenerate gas and classical heat capacity, which is well known. CV classical equals 2/3/2n. Let us observe the ratio. Let us compute the ratio CV divided by CV classical. Okay, 1/2 divided by 3/2, it's 1/3 p squared. N and n cancel each other, and we have theta divided by nu sub 0. For the degenerate gas, this ratio is much less than 1. So this ratio is much less than 1. This has an important consequence in physics. For example, when we consider, when in metals, we have the lattice, the crystal lattice with ions of metal inside and electron gas surrounding them. And the measures say that the experimental measurements of heat capacity of metals tells us that the electron gas has zero heat capacity, maybe very low heat capacity. This happens because it is degenerate, and we see that its value of heat capacity very small with respect to the, let's say, the heat capacity of crystal lattice, which has classical value heat capacity. So that's why we do not see, we do not observe we didn't observe the contribution of electron gas into the heat capacity of metal. And now we should consider a concrete example of degenerate Fermi gas. It's an electron gas in metals. And now here I want to make exact estimates of the thermodynamic parameters of the gas. So we consider electron gas, electron gas. The spin of the particles equals to 1/2, and spin degeneracy equals to 2. Okay. The chemical potential at 0 temperature, or another name for this quantity, which we mentioned, it is a Fermi energy, reads. Now I make simplifications, which you can make yourself. The typical concentration and divided by V of free electrons in metals have the order of magnitude 10 to the 28th, 10 to the 29th meters to the minus third power. Now sub-0 equals 210 electrons. Let me mention that energetic temperature equals like 300 of electron volts for the usual thermodynamic temperature, 300 of kelvins. The ratio theta divided by mu sub-0 is around 100. It is much less than 1. So we have to conclude that gas is degenerate. And the degeneracy condition is satisfied very well. And for 0 temperature, we have the internal. For 0 temperature, we have internal energy 3,5 mu sub-0 n. You can compute this value if you want. And for the pressure at 0 temperature, here it's temperature 0 equals to, okay, P equals to P sub-0. As we know, the pressure, the gas has a weak dependence on temperature. It's like 10 to the 5th powers of atmospheres. And my question to the lecture room, why we do not feel this pressure when we touch the metal? It's my question to the lecture room. Atmospheres, 10 to the 5th power of atmospheres. Standard pressure is 1 atmosphere. It's 100,000 times bigger than. Yeah. It's in pascals, 10 to the 1st. Okay. Why we do not see this pressure when I touch the metal? I touch the metal board. Why I do not feel this pressure? It's very high. the reason is that the electrons are kept inside of metal because of Coulomb interaction with ions of crystal lattice. So the electrons are kept in the metal by the Coulomb interactions with ions of metal. And the second question of this observation is following. If the electrons interact with ions of metals, if the electrons interact with each other, why we apply the ideal gas model to the electron gas? They have strong interaction. Why do we use the model of ideal gas? And now, to explain why it's possible, let us make an estimate of the Coulomb energy, the energy of electromagnetic interaction between the ion in the crystal lattice. So I consider the metal something like this. I have a crystal lattice here, and the positions of ions is more or less fixed. They can oscillate, but they can't leave. They can't leave their position. And here, electrons that can freely move around the ions of metals. So let me forget about interactions between electrons and electrons. It has the same magnitude that between the interaction of electrons and ions. So I estimate the energy of interaction between electron and ion. It means it has U, the energy of Coulomb interaction can be represented as follows. Here, Z is the charge of ion, E is the elementary electrical charge, and R is the distance, let's say some average distance between electron and ion. I can estimate very roughly that the distance has the order n divided by v and multiplied by z to z. Okay, how I obtain? If I set z to unit, it's just concentrations of electrons. It's just cubic root of concentration. So it's some kind of let's say some kind of cube, some kind of size of cube which contains one electron. And I put Z here I put Z here because each ion produces Z multiplied by because the number because each ion produces Z electrons. this ion produces these electrons, Z electrons. So I have the following estimate for the Coulomb energy. Z to the power 2/3 E squared N divided by V to the power 1, or not, to the power 1/3. 1/3. I can say that my gas is free if the energy of a single electron, let's say.
Дмитрий Сергеевич, тогда там V разделить на N, наверное.
Okay, let me. Okay, V divided by N. Okay, thank you. V divided by N. You're right, absolutely right. Okay, and let me write here U small, because it's an energy for one electron. The internal energy for one electron, we denote it by epsilon with bar. It's U, and I can estimate it, replace it by 0 temperature though. So it's like 2/3 of mu sub 0. And I know the value of mu. I can write, okay, where is mu sub 0? 3/10 H bar divided by N, 3 pi N divided by V to the power 2/3. The gas is free. Gas is free if the energy of Coulomb interaction of a single electron is much less than its kinetic energy. And we can divide these two guys. Z to the power 2/3 E squared V divided by N to the power 1/3 divided by, okay, 3/10 H bar squared divided by M divided by 3 pi N divided by V to the power 2/3. Okay. Stop. Okay. So I made a mistake. I made a mistake here. Here should be V divided by Zn. And here should be ZV divided by N. Because distance have a dimension of length, and this guy should have a dimension of length. So I made a mistake, sorry. Here should be this one. Okay, and this is correct. Let me explain. Why this is correct. So N is a number of electrons. N divided by V is a number of electrons in a unit volume. Z is a charge of ion. So this ratio without 1/3 is a volume for one ion. It's a volume of space for one ion. When we take a cubic root of this expression, we gave the length, the size of this cube. Okay, and here misprint n divided by v. And now I can make simplifications. So here 10 thirds m divided by h bar to the first power to the second power e squared, okay, squared v divided, okay, not v, okay. So okay, I have 3 pi to the power 2 thirds here. And look here, and divided by v to the power 1/3, and here to the power 2/3. So I have n v divided by n to the power 1/3. All these guys are parameters of the model. That just include mass of electron and mass of okay, not mass. All these guys have information about determined by the electron. Electron mass is a constant, and electron charge is a well-known physical constant too. So we know this quantity from outset, and here is a concentration of electrons. It's the model parameters. We see that it's proportional to the inverse concentration of electrons to the power 1/3. This means that the higher concentration of electrons, the lower this ratio. So the free electron models works very good for metals with high concentration of free electrons. And see that here is it. So it's very high concentration of free electrons. It's possible to make estimates, and here we get something like this. It's it's equal or less to unit. Okay. Cover? We make a break in 2 minutes. Let me finish with this formula. Okay, for concentration of free electrons, to this, which is in metals, which is observed in metals. Okay, and we see, and thus explains the free electron approximation. And the final thing I want to attract your attention, final point, which I want to explain here, is the heat capacity of the electron gas. Once the ratio theta divided by mu sub 0 is around 1/100, the heat capacity of electron gas is very small, and its heat capacity much less than predicted by the classical formula. At this point, we finish consideration of degenerate Fermi gas, and we are making a break. 5 minutes break. If you have questions, you can ask me. Да, я думаю, нормально.
Сок стоит. Я попросил ему купить, взял бутылку, коробку.
Я понимаю. Я вот можно? Правильно, что ты сделал?
Он бы там сейчас сколько изменилось. Они пропорциональные единицы. Причем, если вот 5 единиц положить, то дает только вот единицу, вот 2 единицу.
Ну,
Да, все было.
отлично. Ну, это
Несколько початок.
Ну, пришли. Ты знаешь, как они присылаются печатки? Знаешь, как присылаются печатки? Вот смотри, самый лучший вариант — распечатать текст, возьми красную ручку.
Понял, да. Как в том
Да, конечно. Они обучают.
скриншотами просто делают.
Сделай, как тебе удобно. Захар, счастливо. Борис, ты готов переводить?
Да?
Те, кто слушает лекцию, давайте начнем сейчас. Просто я хотел тему рассказать. Успеваем? Можем начать сейчас?
Ну, думаю, да.
Так, ну все, давайте начнем. Я думаю, как раз сейчас время. Окей. And now let us turn to the degenerate gas of Bose particles. Degenerate Bose gas. The Bose statistics for the occupation numbers, statistics for the occupation numbers it's n of epsilon. Here, epsilon is the energy of the state, equals to 1 divided to exponent, and here energy minus mu divided by theta minus 1. And we know, and from the general considerations, we know, okay, what's one? From the end, we know that the Bose particles have no Pauli exclusion principle. So a big number of particles can occupy, so infinitely big number of particles can occupy a particular state. The shape of the formula for the Bose statistics tells us that the biggest number of particles is observed as the lower energy limit. So it's so-called ground state. So the biggest number of Bose particles is observed at the ground state. And the number of particles at the ground state is not bounded and is not bounded from below, because the difference exponent because this expression tends to 0. Can be very, very small. And we observe a special phenomenon when mu, by mu I mean the chemical potential, tends to 0. You can, to be correct, you can write -0, because we know that the chemical potential is always negative for Bose particles. And in this case, the average number of particles in the ground state is not limited. Okay, by this infinity is understood in very piquant case sense. So I understand that the number of particles, okay, not plus infinity, let's say plus 2n. N is the total number of particles in the system. So at zero temperature, we can have all particles on the ground state. And when this this special behavior has a place when chemical potential tends to 0. And the very special thing is that mu tends to 0 at non-zero temperature, which can be understood as a degeneracy temperature. Let us estimate the temperature of degeneration for Bose particles, for Bose gas. So we know the expression, we know the relation between the total number of particles and chemical potential. 2 pi 2m theta to the power 3/2. Here 2 pi h bar to the third power from 0 to infinity, x to the power 1/2 exponent to x minus mu divided by theta minus 1. And here the x. We are going to determine the temperature for which chemical potential becomes, let's say, becomes 0. So we can do the following. Once the value of chemical potential is known, I put mu equals to 0 here. And then I get something like this. Now I get the relation between the particle number and temperature, which can be solved. This integral can be found in several textbooks and so on, and it equals its numerical value 2.3 pi, 2 and 315 thousandths. There are many. There are many other numbers. Substituting this value of integral here and expressing temperature from here, I find the temperature of Bose gas degeneration, which equals 331 divided to GS power 2/3 h bar squared divided to 2m and divided by v to the power 2/3. I do not specify details, so, and it's better we have here a question. I put here asterisks. That means that it's not a general temperature, but a temperature of degeneration. For temperatures lower than this temperature, a big number of particles can be observed at the ground state. Okay, the value theta asked is indeed very, very small. If we take mass of atom around 100 atom units of mass and concentration and divided by V of order 10 to the 28th centimeters minus third, we get theta asked equals to something multiplied to 10 minus 8 of kelvins. So it's very, very small temperature. But let us now consider the temperatures below the temperature of degeneration. For temperatures higher than the degeneration temperature, we can consider that we can say that gas is non-degenerate, and we can use approximation of rarefied ideal gas. Now we are interested in degenerate gases. In the degenerate low temperatures, we're interested in low temperatures. Okay, theta less than theta ast. And first thing which we do is a plot. We're going to make a plot. Okay, not here, but it's better right here. A plot of chemical potential as a function of temperature. Here is a temperature. Here is a chemical potential. And here I put the temperature of degeneration, theta ast. For the temperatures higher than theta ast, the chemical potential has certain negative value, and it decreases with the temperature. Let me just avoid the proof of this fact. It's quite easy. But for temperatures lower than theta ast, the temperature, the chemical potential can't be positive, because it's always negative for both the gas. So it's a negative. On the other hand, the chemical potential cannot be a negative value, because theta ast is the lowest temperature when the chemical potential can have negative value. We can't increase the number of states for the particle for lower temperatures. So we should say that, okay, here let me put less than equal to 0. And here, okay, let me here. On the other hand, we can say that it can't be negative, because of this relation. So combining both effects, I see contradiction. I can't satisfy both effects here. To solve the problem appears because the standard formulas for ideal quantum gas ignore the vacuum state, ignore the state for the low energy. Please note that the integration measure here is x to 1/2 dx, and x equals to energy divided by theta. So if substituting here, I have here 1 theta squared, energy to the power 1/2 d epsilon. And this guy equals 0 if energy set to 0. The energy is, if we put energy to 0 and x to 0 here. This means that this expression ignores the vacuum state. The state ignores the state with the lowest energy. And the particles and the real distribution of the particles described not by this law, we should take into account the vacuum state. So the particles lie on, the particles lie in two places. In vacuum state, either maybe let's make in vacuum state, ground state. And the number of particles I denote by N0. And the other particles I lie on the next unexcited state. And I denote the number of excited particles by N ast. And the number of particles on excited states is determined by this formula with chemical potential with zero chemical potential. Because it should be equal to zero. And the remaining particles lie on the ground state. And the number of particles on the ground state is determined by the Bose statistics as follows. GS, here I put the chemical potential, not put the chemical potential to zero. And I can here, as far as I know, the chemical potential should be very small. I can expand the exponent into the Taylor series. And here I interested only in the third order, the first order of expansion. And from here I see that chemical potential equals mu. Mu equals to multiplied by let me theta divided by mu, and from here GS theta divided by n sub 0.
Дмитрий Сергеевич, вот тут вообще, откуда эта формула взялась? GS, это, и почему она становится звездочкой, он там появилась, там, она то же самое.
Let me explain. We have observed that this formula ignores ground state. So we should say.
Так подождите, основное состояние или вакуумное состояние?
Ground state, основное состояние.
И она его игнорирует.
It ignores the ground state because ground state corresponds energy to zero and the same x to zero. For x equals 0, we have zero contribution in this integral. So this formula ignores ground state. And the correct interpretation for this formula is that it takes into account only excited states. Only it counts the particles on the excited states.
Тогда при чем тут вот вы говорили про вакуумное состояние? Это при чем?
Okay, it was a mistake. It was my mistake. Just it was my mistake. We consider only ground state. And now we consider ground state. To compute the number of particles at the ground state, we should use Bose statistics. For the ground state, it has zero energy. Average number of particles at zero energy equals to epsilon divided minus mu divided by theta minus 1. We know that and it is the number of particles in a single quantum state with zero energy. Okay, state with zero energy. We know that the states for the particle with non-zero spin are degenerate G sub s times. So we have G sub s states with zero energy. The number of particles in this state is determined by, in each state, is determined by this formula. So in the ground, so the number of particles in the state with zero energy is Gs times higher. In this relation. So, okay. And from here, I derive this formula. Please note that I used expansions that divided by theta, much less by the absolute value than 1. Now I can determine the correct dependence of chemical potential on the temperature. Here, for temperature then low than theta asked, and here minus. Chemical potential is determined by this formula. It has a very small negative number. In fact, we'll see that chemical potential is a macroscopically small number. Macroscopically, by saying macroscopically, I mean the following. Here, the n sub 0 is a number of particles in the ground state. If this number of particles is a macroscopic value, it should be increased with the particle number. And according to the thermodynamic limit, we consider very big systems. So for very big systems, n is very big, n sub 0 should be very big, and chemical potential should be very small. It equals to 0. It tends to 0 in thermodynamic limit in case of very, very big systems. And once we consider the systems is very big, we put chemical potential here to 0, because this expression depends on smoothly on chemical potential, and we can take thermodynamic limit here just by setting chemical potential to 0. Let us now determine the dependence of n sub 0, number of particles of ground state on the temperature. Let us represent the total number of particles as the sum of number of particles in ground state and number of particles.
Можно еще раз спросить?
Okay.
Вот там выражение для μ, вот, которое слева, вот, минус GS, это разделить на 0.
Okay.
Это же получается μ при температуре вырожденности.
So it's for degenerate temperatures.
Ну, то есть там должно быть θ со звездочкой, по идее.
No.
Или...
It's temperature, but it's valid for temperatures less than degeneracy temperature. No, chemical potential depends on temperature. But this formula is valid for temperatures lower than degeneracy temperature. And now let us apply this formula. And let us apply, and now we know, and now we have the, well, let us use the representation for the number of particles in excited states. Using several simplifications, which I do not want to do here, I can find that n, I can represent n asterisk as n multiplied by theta divided by theta asterisk to the power 3/2. The reason is that it just follows from the definition of theta asterisk. So I have the following: n multiplied by theta to the theta asterisk to the power 3/2. From here, I find n sub 0 equals to n multiplied by n minus theta divided by theta asterisk to the power 3/2. Okay. This formula tells us that for theta equals to the degeneracy temperature, the number of particles on the ground state is macroscopically small. It can be set to 0. It's very small with respect to the total number of particles in the system. And for theta equals to 0, n equals to n sub 0. For 0 temperature, all the particles are on the ground state. In thermodynamics, the collective of particles on the ground state is called Bose condensate. This formula tells us that for temperatures lower than temperature we have Bose condensate. for temperatures lower than the degeneracy temperature. And the size and this formula determines the law, the dependence of particles in condensate on temperature. And for zero temperature, all the particles in gas form condensate. Okay. Now we are going to compute the heat capacity and internal energy of the Bose gas. Okay, in case. These particles in ground state have zero energy, so they do not contribute to the internal energy. And internal energy of the particles on excited states equals to the internal energy of the system. Okay. Here should be V, and I correct the formula. We have V theta. And this is, and here should be power 3/2. Again, this integral is a sum constant. So again, this integral is a constant, and we can find the energy of the Bose gas. Just I omit all the simplifications. I just write the final expression and multiply it by theta divided by thetaast to the power 3/2. Here we see the temperature dependence. Here theta to the power 5 seconds. Here appears this one. And here and let me present the numerical value of the integral. -1. Okay, 1.783. Our main conclusion here is that the internal energy is proportional to the degree to the temperature 5 seconds. Now we can compute the heat capacity of the gas, adjust derivative of internal energy for temperature for constant V and M. And here we get, when we differentiate, we get 5 seconds. So 0 here multiplied by 5 seconds and theta by theta ast to the power 3/2. And I want to attract your attention to the value of this numerical factor. When I multiplied, let's estimate this factor. It's approximately like 0.8 multiplied by 5 seconds. So it's in average, let's say it's like 2. Okay, I'm not correct here. It's like 2 n theta to the theta ast to the power 3/2. Keeping in mind that the heat capacity is determined by the time temperature derivative of entropy, we can easily find the entropy of the gas. It's like 5/3 U divided by temperature, and it's proportional to the temperature to the power 3/2. Here we see, and it's easy to see that the entropy should be 0 for 0 temperature, so the integration constant is 0. And let me make several important conclusions of my observation. The first important conclusion here is that is the dependence of heat capacity on the temperature. Let me draw a plot. Let me draw a plot here. Here, temperature, and here, heat capacity. Let me write specific heat capacity, so it's divided by N. And here, let me write 2. 2 is this 2. And here is 3/2. Is the classical value of specific heat capacity. And let me write, and here is the degeneracy temperature. When the gas is degenerate, I have a degree, a dependence of heat capacity like theta to the power 3/2. So it increases here. Increases for theta from 0 to theta ast. The classical value of heat capacity is its heat capacity of very hot gas is 3/2. So heat capacity should change in some way here. It can be shown that it's continuous, but its derivative it has a discontinuity. So this one. We know that for rarefied Bose gas, the temperature is slightly higher than its classical value. And this decrease of heat capacity is described by the formulas for rarefied gas. Rarefied gas. And this increase of heat capacity, it's due to destruction of Bose condensate. And we have higher capacity values in the classical case because we need to to you to absorb more energy to describe Bose condensate. And what is important, that the temperature derivative of heat capacity for constant V and N has discontinuity here. Before it's positive and after it's negative. So we have a phase transition at this point. So we have phase transition at the degenerate temperature. It has a third order because the third derivatives of thermodynamic potentials have a discontinuity. Third, entropy is first, heat capacity is second, and the derivative of heat capacity is third. This is a difference between Bose gas and Fermi gas. When we increase the temperature of Fermi gas, its properties smoothly change. And we have a smooth transition between degenerate Fermi gas and let's say, classical or hot quantum gas of fermions. In Bose case, we have some kind of phase transition between a state of condensate with condensate and state without condensate. So we have maybe I may say we have just okay, we have difference, we have easily observed difference between degenerate gas and non-degenerate gas. The gas in degenerate is degenerate when we have a Bose condensate. Okay. And final computation, which okay. One very important comment. One very important comment is the following. We're talking about Bose condensate, but Bose condensation of free gas. And sometimes we observe that particles, just like images with particles that form a cluster and so on. This does not happen. The localization of the particles does not happen for free ideal gas because its states are plane waves and we have no selected space-time point where my particles collect. So for a free gas, Bose condensation happens not in a such form. It happens, maybe let's say, is moment of space. It happens in space, is moment of space. And Bose condensate is determined by the particles with lowest value of the moment. My final comment relates to the pressure of Bose gas with condensate. We know that pressure equals to the ratio of chemical potential divided by volume.
Дмитрий Сергеевич, пора уже закончилась. 5 минут. Как?
Okay, 1 minute and we finalize. And only excited particles produce pressure. And this equals to 3/2 divided by V. So I can say U here, forget about here, and forget about here. And this value is proportional to the temperature to the power 5 seconds. Okay, thank you to everybody. If you have questions, you may ask me.